I think it's time to start. Hello, welcome everybody. I'm Alexander Kanevskiy. I started to work in CNCF or Kubernetes related projects about 3 years ago. Initially I started to work on things related to C cluster lifecycle, like how to install a Kubernetes on bare metal. And a bit later I started to look at different kind of device plugins, again, like how to use accelerators. And over the time I got interested in the topics related to resource management. So one thing what we are going to talk today, it's in this area. So noisy neighbors. So we know what noisy neighbors is like. Like it's your neighbor with a hammer drill trying to do some renovation in the morning, like drunken company in the restaurant and so on. Even right now, for us, like the noisy neighbor is about our time. So, for example, like Nokia folks at the same time as my slot were doing talk related to 5G and for time-critical applications, so very close to what I will be talking about. And what I wanted to say is what these kind of problems were unique to all of us. I mean, so really, the silver bullet doesn't exist. So you have in your cluster your own problems. The person sitting on the chair next to you, you have a bit different problem. So what I'm going to talk today, what is out of scope is if you can mitigate it somehow by adding more nodes, spreading workloads around your cluster. So it's not a problem, it's expense, like how much you can afford to buy a new hardware. However, what is in the scope of this talk today is about one single node. So you get workloads scheduled, you have some of the hardware resources on your node, like its CPU, memory, yada yada. And now those different workloads were misbehaving with each other. So practically we are like playing with Tetris on the same node. Like, but the figures what we are using is like, it's not simple two-dimensional figures. Like every resource, everything what you are using, it's pulling the figure to different place. And you also, like, the perfect line doesn't disappear. Your figures over the time are changing the shape during the execution. Another thing what is also in the scope today, so we are in the runtimes track. So what I'm going today to talk, it's about like CRI-O, containerd, OCI spec, runc. Unfortunately, I'm limited in my time, so I cannot talk about like kata, gvisor, and so on, but we will try to keep in the like smaller scope, which is most common for everybody. One small note, so if you are in production still using the kubelet directly talking to the Docker, so this Docker shim, well, I have a bad news for you, like sorry, you cannot do much with it, so probably you want to switch to something better like CRI-O or containerd in your setup. All right, so let's talk about hardware resources. Just a standard picture, you know, like most common server, like 2 sockets, you have a bunch of cores, you have some memory, you have interconnect, you have some accelerator devices. So raise your hand what you think like it's real world picture. Okay, not that many, good. So now let me scare you. So indeed, in the real world, the situation is a lot more complex. So you have a sockets, and inside your sockets you have a physical cores. It can be one chip, it can be multiple chips within one socket. You can have different sizes of the cores. So for example, like in your phones, most probably you have a like big little architecture. When you can have the machines which have like one or more thread on the physical cores. Your physical cores can run on different speeds, so like not all the cores are in reality equal. When interconnect between the CPUs, again, when people are usually saying like, I have a NUMA problem, usually what we mean is actually one of those interconnect is get saturated by like data transfers. And amount of this interconnect, it will be really dependent on your, of your server architecture, of like the model of CPUs you are using, and so on. And if we are talking about the NUMA problem as is, so the key part about NUMA is the letter M, the memory access. So you have multiple memory controllers on your CPUs. So you might have different setups of a memory. You can have like normal memory plus persistent memory, which is a bit slower, or vice versa. You can have a normal memory and high bandwidth memory. And for kubelet, it will be seen as a like normal memory all together. But in reality, for your workloads, it might have a difference. Another thing is what, like, when people are thinking about NUMA, it's like, well, it's memory plus CPU. It's a wrong assumption. So you might have completely legged NUMA node completely without cores. So NUMA describes how your memory layout in the system is done. So when you have devices, it's connected to PCIe buses. When you have interconnect between those devices, you probably, like kubelet or your orchestration doesn't really know. Those devices can be connected not only through PCI, but our resources. And then, of course, you have also like all your integrated things like network, blkio, storage, and so on. So the reason why I wanted to show this picture is actually like to notice all those errors. So all those errors is your like toll bridges. Every time you crossing them, you are paying the cost. So mitigation of those things is actually trying to combine the workloads of how to minimize going through those, or how to find the optimal route to minimize that cost. So let's look how the Kubernetes thinks about the resources. We have on the first level, like, well, native resources like CPU and memory. And as I said, like for Kubernetes, CPU and memory are equal. So if you want to try to express, I want a cores with a bit faster speeds, or I want one physical core or one physical thread, or higher bandwidth memory, you cannot do it. Of course, you can do like some kind of leverage of extended resources or device plugins, but usually for native resources, you end up with double bookkeeping, which usually doesn't end up well. You can use something what, like to make decisions from the pod class, like some artificial thing which implicitly done by Kubernetes looking at your native resources. Good, but if you have some scenarios where like sidecar injected and so on, it easily gets screwed up. Another way how to enforce resources is using the metadata of a pod, so like labels, annotations. And I would say most of the time it's not only used, but sometimes it's even abused annotations model. So like example, like network guys are using it for setting the memory network bandwidth. SecComp guys, we say like, well, use this profile, and actually in the background, we expand it like to a huge list of values. And the problem with annotation is what it's visible to the user, and you need to think how you actually will be exposing, like what is the user experience of this thing is going to be. And the most bigger problem is what when you're trying to expose resources which a bit more complex than just like one single parameter. Example of blkio. So imagine you have a workloads which are competing on the storage, and you need somehow to prioritize it. So in OCI spec, you can say like, well, we have a weight, and when, if you go down to the kernel level, well, kernel understands what you can have weight per device. You can set amount of IOPS or bandwidth, again, per device. So if you try to expose all of these parameters to the user will say like, oh, well, thank you, no. So you need somehow to find the balance. So for example, like create a class like blkio bronze, silver, gold, and then in the background, try to convert it on the node level, like this class name to specific parameters to a specific device on that node. Because again, you can have on the node, well, you can have heterogeneous cluster where like the nodes have a bit differences in the hardware. Another complex resource which I wanted to bring into this example is well, Linux kernel has a file system which is called like resource control. What it allows to do, it allows you control the allocation and monitoring of layer 3 caches and the memory bandwidth. And difference with the C group is what, like in case of C group, you can easily, like it's software, you can do like as many groups as you want. In case of this resource control, it's all hardware dependent. So you have, well, 16 different classes, but that's it, you cannot create more than that. And another thing is, to control the parameters inside, you really need to understand like what kind of hardware behind of this thing you have. So again, you need to think not only how to treat the resources of what hardware gives to you, but also how to present it to a user and how to do a mapping between those two things. So how we can control those things? First of all, let's look at our nice three-layered cake. So on the bottom we have the runtimes like runc, kata, divisor, and so on. We have a layer between those, like OCI spec. On top we have runtimes, like most common used, like container D and CRI-O. And then we have one more layer of interfaces, CRI interface, and then we have a kubelet. So each of those is responsible for own things. But the interesting thing here, so if you look precisely, so the more you're going down, the more it knows about the hardware, the more it knows about the control, so even more you can do. The only problem is what the information about actually what user wanted, it's all above the kubelet. And the reason is those interfaces between those are not passing all of the information. So for example, like if we look at the CRI interface. So CRI interface says like this is where your CPU parameters, this is the memory limit, this is the CPU set which you need to use, this is the memory set which you need to use. And if you noticed, there are a few things missing. So one thing is, so for example, like CPU request and limits, where you don't know. You can reverse calculate it from the CFS shares, but you don't have it. Memory request, you know what the limit is will be, but you already lost the information how much user actually wanted to have at minimum. And then all the extended resources, kubelet doesn't share those. It calculates it itself and keeps it by itself. The huge pages, kubelet says like, oh, well, runtime, I know you can handle it, but thank you, I will do it myself. And in case of CPU set memory, we have it in the spec, but it's not used. Well, maybe in the future, like with introduction of topology manager, and maybe soon we will have like something for memory, we will have usage of that, but right now it's not used. And if we go down to OCI level, so for example, if we take runc, like I know a container ID, I want to update some of the resources. Like beside the things what CRI already communicated down to the runc level, I can do a few more things. Like I can set the blkio weight. I can tweak like kernel memory parameters, for example, like for TCP stack. I can set L3 caches and memory bandwidth schema. But again, the problem with L3 caches, it will be per container. So like using that interface, you can set it only like for limited amount of containers. And next thing, if you're somehow able to intercept the OCI spec, like the config, what runc get before a container created, you can see what you have a few more parameters what you can control. So like cache classes can be done properly. Another thing which is super important in OCI spec is actually you can control execution of the hooks. And the hooks on OCI level, it's the first thing where you can plug your own custom policies to do something. So what is it? It's a simple like binary or script or whatever. You configure what on which stage of a container lifetime you need to execute it. You define the arguments, what needs to be passed. It's called by the runtime itself. It's called in the host namespace, so you can tweak, for example, the C groups of a container. But what you cannot actually touch is actually the config of a container itself. So if you want to inject more mounts, if you want to inject more devices, well, you are not completely out of luck. You can do it by yourself, all this mknode and C groups filtering, but well, not easy. We have few hooks defined right now in OCI spec, and there is a PR from NVIDIA to actually add even more of those. Might be useful. Might be you can do something with it. How to enable it? So in CRI-O, it's easy. It's disabled by default, but you can easily comment out one line, and it will start to look for configuration options where to find the hook. So it looks for like quite simple JSON file, which says like, well, on these stages, execute this hook, and you can say execute it always, or you can execute it only if particular annotation is passed, but that's simple in case of CRI-O. In case of containerd, unfortunately, it's not that easy. So this functionality does not exist, but soon I really hope that it will be exist. And thanks to Mike Brown, which actually helping to get it done. But again, like it's a hooks. You can do certain amount, but you are limited. So the next thing, what if you want to do a bit more complex thing? You need to go a bit level up. So you need to define your custom runtime. And custom runtime, thanks to Kubernetes' latest features, it's quite easy. So like runtime class, you define like, well, I have a runtime which is aware of blkio. It will be handled by handler called blkio. In my pod, I can say, well, use runtime class for this pod. And on level below, in CRI-O, you say, well, this blkio handler is actually this binary what you need to call. In containerd, it's almost the same. The difference is like, oh, well, actually, a couple of underwater stones. So first of all, containerd supports two kind of interaction with the actual runtime. So you have OCI, exec-based interface, or you have gRPC. So in this scenario, you can see what it's about the previous like exec-based interface. Another thing, like if you're trying to pass the parameters using annotations, you need to make sure what you instruct containerd of actually which annotation needs to be passed down. CRI-O in that sense, like it's passing almost everything what it knows. There are some exceptions how you can find particular annotation for per container, but it passes. Containerd require these additional configuration options. And when I'm talking about like the special runtime, I'm actually talking about like quite simple script or quite simple binary. So it's something approach close to what NVIDIA guys are doing. So you are practically wrapping the existing runtime or shimming, whatever you prefer to call it. In this particular example, what I have, I just created a simple shell script. Like for all runc commands, I'm just passing it. But before the container start operations, I want to enforce some of resources. And what I do, in start operation, I know the container ID. So out of container ID, I can request the state of it. From the state, I can get to a config. From the config, I can get the name of the C group, and this is the place where the kubelet actually tells me about like what kind of QoS classes it is. So guaranteed, burstable, or best effort. And in this particular scenario, so I'm saying like, okay, well, guaranteed, I don't touch it. For burstable or best effort, I am lowering the priority of blkio operations using the standard runc update command. Trivial, works. There are a few problems with that. One of the problems is that like, you need to maintain those wrappers. You need to, like, for example, this code, it has bugs about parsing the parameters. You need to be careful with that. Another thing is, you have one runtime class per pod. So if you have multiple scenarios which needs to be handled, you're out of luck, or you need to have your own special, let's say, like default runtime class, which will be handling all of those. So we thought about that, and we tried to do different experiments on how to control the resources what I showed to you, like caches, memory, blkio, yada yada. And we realized that what hooking into lower levels, it might help, but we not necessarily have enough of information. So we know about containers, we not necessarily know about the higher level, like pods. And we, some time ago, we created a tool, or actually open sourced our internal tool. We call it CRI Resource Manager. So what is it? To put it simply, it's a proxy for CRI. So it takes request from kubelet, it passes it to containerd. So what it does, besides proxying those things, what it actually also can do, it can enforce certain decisions. So for example, like setting the memory things, or injecting more mounts, or like trying to shift something, or actually even do something what is not part of OCI spec, or like talking directly to the kernel about changing those parameters. So I yesterday heard the talk from Uber. We did something similar actually to migrate from way MES is set up to Kubernetes, again to enforce like local policies, what we need to have with the logger interface. So again, why? Most people would say like, well guys, why are you doing a separate tool? Like why are you not doing it upstream? I need to say a history about this tool. This tool started as an internal debugging tool. We just wanted to understand like, well, we have standard cluster setup, Kubernetes, non-patched, we have CRI-O, containerd, again, non-patched, something goes wrong, we need to debug it. So we started with just like, let's add tracing. We found the issue what we actually wanted in kubelet, and when we realized that, okay, well, if kubelet will do something XYZ, can we simulate it with that tool? And this is how this tool will get a bit more developed. We are using this tool as a proof of concept work, so we can try something, and afterwards we can, together with the data, we can go upstream and propose those changes to the kubelet. Architecturally-wise, it's quite simple. So, like the proxy part is, as I said, well, get it, pass it, log, trace, and so on. The interesting part starts a bit later. So we have a set of internal policy engines. You can, by these policies, actually, you have all the information what is passed on CRI for both pod and containers. You can modify it directly. You can go to C groups, or for example, like resctrl, as I mentioned. We are also created downwards API. So for example, if we do some decisions, we want to inform the workload about the decisions what we made. And if we do something dynamically, again, workload can monitor with downwards API file and get information about it. Another thing which is also most important what we are trying to do is actually we want this tool not to be maintained as a set of static policies, but also give you a possibility to try your own thing. So for example, like Netflix, we have idea of Titus project where you can say, like we have a machine learning actually, how the workload needs to be placed within the node. We want to give you a tool which gives you possibility to experiment with similar kind of decision. And this kind of dynamic interface also serves as on a purpose of trying to do like dynamic reconfiguration of the nodes. So what we can do now, We started with a simple policies. So we decided like, okay, well, let's take the static policy out of kubelet, and what if the kubelet will be supporting isol CPUs? Does it give the workload proper like performance gains? So we added support of isol CPUs in our external policy. It worked. When we start to think, okay, well, what if workload is clever enough to ask not like 2 exclusive CPUs, but like 2.5. And 2 will be used exclusively for data threads, and 0.5 from the shared pool can be used as controller threads of your application. So we added this kind of policy, and this is where this downwards API came saying we are communicating like those are your exclusive ones, and those are your shared pool. And the last thing what we have from a policy perspective is a topology aware thing. So I know we have a topology manager inside the kubelet right now. It mostly works about aligning devices and aligning the CPUs, but we want to have few more steps forward. So we able to detect what kind of storage you are using, and we are trying to move your workload like closer to your storage. So like you can get from, for example, like from NVMe disks where the best of your performance. We are aware of like will the workload feeds into one memory controller. If not, we can try to find like a hierarchy on top, still to feed, still to minimize the cost of your workload to be operational. And another thing which we also try to experiment, and I hope to see it someday in the Kubernetes actually, we have cross-container affinity, anti-affinity. So for example, if you have like 2 containers in your pod which does a lot of IPC, you want to keep it close. But if you have like 3rd container logger, which is low priority and shouldn't be too much affecting, you probably will want to move it to separate memory node, to separate cores out of it. And it works not only within like one pod scope, because we are in CRI level, we practically know everything what kubelet is knowing. Like all the pods, all the containers, what is running, and the whole view of the system. What we also have, we have support for memory and caches. So you can define your own classes. You can map it to like with best effort and so on, QAS classes from kubelet. And you can set the parameters like how much you want for each of the class. And what we also have right now is the dynamic API. So like if you have a heterogeneous cluster, you can define like, well, this is the default for all the nodes, this is the config for group of your nodes, and this is the individual config of this particular node. And you can dynamically change it, it will adopt, it will rebalance based on the settings. What we don't yet have, but I really hope to do it quite soon, is what we haven't finished the blkio implementation, but it will be similar to caches and memory. So you will have a classes, for each class you will have parameters per device and when you have. What we also want to experiment is about, like we are hardware guys, right? So we have ability to measure the things which, like in how much interconnect is used by certain processes, how much of vector floating unit used by certain processes, how much like this workload causing thermal throttling of a CPU. And we can try to do dynamic rebalancing, like, well, if this is causing with thermal throttling, can we move it somewhere so the rest is not affecting? So this coming next, and I really hope very soon. And last, but of course not least, is external policy API. So all the information what we have, we are ready to share. And if you want to experiment in your data center with your own policies, machine learning, whatever you'd like, go ahead. I don't have time today to show the demos, but the slides are available, links are available, watch a screencast we prepared with a nice set of demos actually showcasing what we can do right now. And to wrap up, the key takeaways, what I would like you to remember from this presentation. So first of all, I know we are in cloud. I know what some of your machines might be virtualized, but still think about the underlying hardware. It's still somebody's computer. You still can predict how it will behave. And keep in mind what, like, architecture of computers are changing quite rapidly. Like assumptions of the hardware, what you had like 10 years back, it's not anymore valid. Even like 5 years back, it's already like many things changed. Second thing, what I wanted to say to you is think about like how orchestrations are actually orchestrating the container, how you represent the resources. Right now, Kubernetes have a very simple model about like countable objects. But if we want to control more fine-tuned resources, we need something more. So think about your experience, think what you want to control, come to the Kubernetes community, let's discuss. And the last and the most important. So I give you hints how you can do it on OCI hooks level, runtime levels, well, CRI-RM, our tool, what we are using for experiments. But what is the most important is what you can try your own ideas. You will have your own results from your real production application and data. And this thing is the most important thing for us as a community to actually design how it will be in the future of Kubernetes. So that's what I wanted to say today. I don't know, have probably a few minutes for the questions. Can we get a microphone?
It looks like you have most of the guts of what Kubelet is doing, with the exception of the external APIs. Have you considered just adding the external APIs so you can be a drop-in replacement for Kubelet?
Yes, we actually, yes, let me answer it that way. It's our long-term goal to improve the CPU manager in Kubelet side to actually do this kind of dynamic policies. But to propose something like that to a Kubelet, we need to come up with a well-designed API. So it's vendor independent, and we need to have a well-qualified data to show like why it's useful. So what we are right now in the stage what we want to collect the data. And with that data, we want to go to Signal community and say like, well, this is how we want to do it. If you can fetch the microphone over here.
So you're talking about Lloyd's neighbor, right?
Yes.
So that resource manager or proxy, those stuff, right? So, but there is some kind of category device, right? Like for example, if I have crypto device or whatever, I want to, in those C group or whatever, runc controller may not can do those Lloyd's label or rate limit, whatever, those kind of stuff, right?
Yes.
So I'm not sure how can we solve that one without particular property.
Well, that's one of the reasons. Let me go back to one slide. It's over here. So it's exactly about like this part. So if your device actually has some of the kernel interfaces which allows you to control the internal resources of that device, you can plug your implementation, which we'll be doing with fine-grained kernel tuning. Or, well, if it's enough on your case, on OCI hook level, you can do it where. It's all the question, like, where do you have enough information to perform this operation? So one of the example, like NVIDIA GPUs in the cloud, it's mostly exclusive usage devices. On our case, with Intel GPUs, it's shareable resource. And right now, Intel and AMD, we are having discussion in Linux kernel community of actually how to come up with proper C groups interface, how to manage the resources of GPU, like time shares, memory, and so on. So if you have your specific like crypto devices, probably you can join the same conversation and see if we can do something like that for your kind of device. All right, so we run out of time. Thank you so much.